Good afternoon, ladies and gentlemen. First of all, I would like to express our sincerest congratulations to the 33rd Asia Conference. So we have seen so many old friends and new friends. It's a very good opportunity to meet together and see what's the new development, new applications. So taking this opportunity, I would like to tell a little about a recent research project on global land economy and centimeters resolution. Now you know that our global is facing big changes. So people were arguing that human has been induced global environmental changes, as what Professor Suchimurai mentioned this morning. We're facing something like serious tsunami and also flooding and less of energy and many others. So our daily life were influenced. And since many years, since about 1980s, people started to study global environmental change. We have already a long research history. There are 4 groups of people, or 4 major programs on that. One is what we said, IGBP, a group of people from geosphere and biosphere working together. The other program is from meteorological people, the World Climate Research Program. The third one is from HDP, and the third one is diversity studies. So many people are working on that. Since about 10 years, remote sensing people stood up, say that, okay, we as remote sensing people, we are going to form a group on Earth observation. We provide data to global environmental studies. So since last year, International Society of Research Council, ICSO, proposed another research initiative called Future Earth. The major idea is to integrate not only natural sciences but also social sciences together to address the global changing problems from a regional scale to global scale. So they would like to provide what they said, a full understanding of global change and its impact. If you look at this diagram from ICSO, they raise 5 basic problems, or we call the grand challenges. The one is forecasting what will be happening, like Professor Suchimurai just said, when will be the next tsunami, how large it will be. The second change is how could we observe the global changes. Then we have confining, responding, and innovation. So it's big changes. Our society, research society, and scientists and the user community need to reply. Among all these elements, you know that land cover and change is one of the most basic data. So, as you know that land cover is different than land use. It's different concept, but it's linked together. Okay, it's one of the key parameters of the Earth system models. Last year, NASA has published a survey saying that land cover is one of the most used Earth observation to geo-social benefits areas. There were 9 social benefit areas. So land cover was ranked as 4th highest ranked observation. So land cover is important, but we don't have enough good land cover data. If you look at the global land cover data, we see that there were 6 data sets already developed. The first one was developed by USGS. The resolution is 1 kilometer. The second one is from the University of Maryland. the third one from the University of Boston University. And we have also 2 from European communities, 1 from Japan. 4 of them are with 1 kilometer resolution. 2 are with 300 millimeters resolution. So the accuracy are not very satisfying. But what I will say here, it's already very good to have all these data sets. It's not easy, because if we like to have a full coverage of high resolution imagery of the globe, it's not easy. So they have achieved good results. These data sets are what we are using today. Okay. So GEO, as a group of Earth observation, they have proposed to develop global land cover data sets at high resolution. Here, when they make high resolution, is less than 50 meters resolution. So GEO proposed to provide a suite of global land cover and land coverage data sets, and they would like to use that for all the 9 social benefits areas of GEO. In this background, China started a project since the beginning of 1910. So the main purpose is to develop data sets at 30 meters resolution for 2 years. One is 2000, the other is 2010. And the other objective is to develop knowledge and methodology for higher resolution global land cover mapping. So it's different than coarse resolution global land cover mapping. And of course, one of the other objectives to contribute to GEO, since China is a member of GEO. So GEO adopted this idea, and this project was listed as one of the key projects of GEO for its 2012 to 2015 work plan. So you know that there are 9, there were 26 tasks, 5 for infrastructure and 6 for institutions and development, and many others for information for societal benefits. So here, global land cover and the change is listed as SBCL2. It's very hot here, so I can take it. See, I have you have here some other tasks. I remember JAXA, the gentleman from JAXA mentioned that Japan has contributed to several tasks like disaster to GEO. So as the president of ISPS, I would say today we have several ISPS people here. Christian Heiberger, Secretary General of ISPS, Xu Jingrai, former president, and Jiao Jun, also former president of ISPS, and Armin Green, on member of ISPS. So ISPS is also contributing to global land cover mapping, and we recently decided to set up a working group on global land cover mapping and services. It's a one working group affiliated to Commission 2, 4, and 8. And we started to prepare a special issue on global land cover mapping for our journal, ISPS journal of remote sensing, for photometric remote sensing. And we start to also collaborate with many other organizations to develop a web-based global land cover mapping, the global land cover geo-processing services. So now I would like to tell you something, the methodology we have developed. If we look at global land cover mapping, people will say that, okay, it's easy. We have learned land cover mapping since we were students, okay? But if we go to the global scale, the thing will be different, because there will be serious problems raised by the global scale. For instance, when you would like to get a full coverage of all the For instance, it's difficult to have a full coverage of good quality of imageries for the whole globe. For a small area, it's easy. You can have a wide choice of good quality of imageries. But if you would like to have imagery of similar season and good quality, no snows, no, clouds, it's very difficult, sometimes impossible. Another way is for data processing. So for all the data sets, you need to do geometric corrections, removing clouds, and also topographic corrections. It's quite difficult, very difficult. A certain way is for classification methods. So people are used to develop automatic classification method approaches, but no one could be suitable for all the imagery in the world. Okay, I mean, for different imagery in different areas, you might use this algorithm, for the other use another one. But for global mapping, it's difficult to choose one single algorithm for classification. So this time we are facing three basic tasks. First one, how could we have full coverage of the Earth with 30 meters imagery and have all the imagery processed? The second one, how could we do landcard classification at 30 meters resolution? So it's different. The third one is validation and data services. So it's three basic tasks. So the basic methodology I have developed is to use 30 meters imagery for the 2 years, 2000 and 2010. If you know that, we have continuous landcard imaging from the United States since 43 years. So the first Landsat was launched 1972. It's 40 years. So this year people celebrated the 40th anniversary of Landsat. So fortunately, USGS has made the announcement and release of Landsat imagery free through internet. People can download all these data sets since October of 2000. So it's one of the basic imagery we can use for global landcard mapping at 30 meters. And many countries are also developing higher resolution imageries. But at 30 meter scale, China has launched what we call the HG satellite. So it's 30 meter resolution and it has a very wide swath. It's 720 meters swath. So what's interesting, it has very similar spectral band as TM. So we can have a good combination of these. We have also some other satellites like Beijing 1 small satellite. So we try to combine these imageries. For the 2000, we use basically TM, okay? And for 2010, we basically use TM and HG satellites from China. Of course, we need to do all the pre-processing. One processing is geometric corrections. And for Chinese HG satellites, we developed specific algorithms to find geometric correction. And the second one is the geometric correction. So it's before the correction, it's after the correction. So it's very useful, necessary for a good classification. And also methodology for topography corrections and cloud removing. For some areas they have very serious clouds, so we try to use substitute imagery 1 year after, and then we apply the algorithm to do that. So this one is before, this one is after cloud removing. So after all this methodology, we should do classification. We have two tracks. The first one is automatic classification, what we call the quick and dirty results. The second one is precise mapping with hierarchical classification approach. Before that, I would say we are using modified land type scheme. We basically, this time, we extract only 10 levels. First the types, that is crop, forest, and grassland, water, shrubs, wetland, tundra, and also artificial and bareland. So 10 basic classes we are working. But also for forest, we try to extract some second classes. So the basic idea of automatic classification is that we select samples, then we do classification with supercomputers. We have applied several different classifiers like MLC and random forest, SVM, many others. Okay. This is the first results by automatic classification. So we have used about 9,000 TM and ETM scenes and 5 supervised classification algorithms. So this is the results of the classification. If you look at this one, the accuracy is something like 70%, less than 70%, okay, for different methodology. So in total, we have applied 40,000 samples for accuracy validation. Okay. But the results are not good enough for us. Why? When you look at this one, you see it's very complex to do classification for imagery at centimeters resolution. If you look at this one, you'll see this is a wetland for some areas in Argentina, okay? And it's for Russia. Even for human interpretation, it's difficult to distinguish which is open water, which is wetland. How could computer do that? And this is some other areas. It's from Brazil, okay? And we have also seasonal rivers and flooded areas and seasonal lakes. So it made the computerized classification very, very difficult. The same happened to cropland. You see, you have different type of morphology, and in different areas, the cropland have different shapes and different texture. It's very difficult to be handled with current computerized classification scheme. So after quite a long time discussing, we decided to develop a precise mapping scheme. That's different than the purely computerized classification. First, we divided the whole globe into about 860 equal zones. So because in each equal zones, you have different landscape, different forest, something like that. We have no idea about that. Then we would like to develop some methodology to extract the features for water, the grassland, like we have a bareland index, and artificial cover index, and NDVI, many things like that. So after that, we try to do classification for every single class. First for water, then artificial cover, cropland. So we try to make things simple. Do classification of single classes, then combine them together. Okay. So during all this process, people could have interactions. So people can check every patch to see if it's the class that we would like to have. So after that, we have the post-classification process. We combine all these together. So we have developed a methodology for each of the items, singles, water, cropland, and built-up area, and bareland, and many others. Just give some examples. For instance, for open water, we have a clear definition of what is open water. Then we develop a technical specification for what we call the specific precise mapping. For instance, for area open water, okay, if it's larger than 3 by 3 pixels, it should be extracted we have a serious, strict approach for validation. And for linear open water, the wide stream view, large density pixels. So the human operators could have good access to that. So we have developed some methodology for extraction of open water. For instance, and here we have something like algorithm with decision tree SVM. So we have human interoperation to extract all the open water patches by patches. The same thing happened to artificial carbon. We developed artificial index, we calculate that, and then we have the rule-based approach. So classification, computerized classification first, and then we have some what we call a manual editing. So it's the results of that. Okay, artificial. When all these single features were extracted, we have a combination, integration of these results. It's better, water, forest, shrubs. When all these are finished, we will have a data product validation. We are developing a web-based system to enable people to look at the image we use for classification and the results. It's also linked to Google Earth, so people could have access to external information. And we have also tools for people to have the corrections. Yeah. So all this has been done by what we call the product-oriented research and development. So it's not a pure research project, but we organize people to work with us as operators. So now we have preliminary results. Firstly, we have completed full coverage of 30 meters for the whole globe. You see here, for the year 2000, we have around 10,200 things. Okay. And for the year 2010, we have 9,900 things collected. And 2,600 things for HDS satellites, because it has a large source. So we have completed image coverage for 2 years. But the question is that we don't have a single temporal. We have a different, you see from here, this color green is imagery taken from summer, from May to July. So it makes a little bit different when we do the classification. So the next step is precise mapping. So we have completed a pilot study, interior test, and open water mapping, wetland mapping. And we're still in the process of some other single classes mapping. The first pilot study we have done is in Shandong province with 5 ecozones. So the classification results is like that. We have about 78% accuracy. Coefficient is 0.7, so it's quite good. If you compare it to some other products, the accuracy has been improved greatly. It's natural because we are working at high resolution. And after that, last year we had the interior product testing. So we asked people from mapping agencies to work with us. So we selected 11 testing areas, different areas, Asia, Africa, Europe. So this is the results for the year 2000. And we have also some results for the year 2010. It's for Africa, Barcelona, for Canada, for Australia. So after that, now we are organizing 5 production units working for 5 different continents, for Asia, for Africa, America. Okay. For the moment, we have finished global land archive mapping for water, open water. Okay. This is the results of the open water. what's interesting to see that since 2010 to 2010, surface water, global surface water has decreased. Not only for the whole globe, but for all the different continents. This is land cover, the land surface water distribution for Africa. The same results has been arrived for Africa. Okay, but what I'm saying that since we have used landscape imageries for different seasons, because we cannot have unique seasonal distribution. So try to use a series of multi-state to have a static correction of mapping results. Okay, we have also A-shaped land surface water distribution. Now we are trying to finish all the other single class landcard mapping. At the same time, we're trying to start data validation before we release the data product. So, as I said, all the data will be provided to the others on the on the web, and we are going to also develop a policy for data sharing and for data updating. So now we have been working with two components of geo tasks. One is global landcard mapping data sets and services. I'm chair of that. The second one is for validation and user engagement, with Stephen from the European Environmental Agency is chair of that. So we are working together to set up a task force for validation. So now I will take this opportunity to call for participation in validation. So first for open water, then to wetland, then to blue harbor areas, and many others. For more information, please go to our website. And I have a few brochures with me if you're interested in that. Next year, we are going to organize a meeting for validation of these products. April 29 to 30. Next year in Beijing, it's immediately after the Acrs conference. So we are going to present the results of the global landcard mapping. We will talk about the validation of the data products. We will talk about also the validation and accuracy, something like that. So finally, we say that now we are facing also great challenges. So we are asked to provide information to decision makers and to users. If you look at this diagram, there's people who are telling us, reporting us, what's the change, what are changing, how fast it is, like the change of the climate, the temperature of the surface. So there are some other people, GIGOS, who are trying to identify what are the basic variables, observations we should do. And we, as remote sensing people, we are asked to provide observations, to provide something like landcard data information to the others. So we have different responsibility. From what I would say that you see, we start to do the first global landcard mapping at high resolution. So USGS, they gave us a good support. So we are going to work together with USGS, with the European community and many others to develop high quality global landcard and change data sets. But we have a long way to go. For instance, people ask us for reliable information, for efficient services, and also they would like to have capacity building and outreach. So the tasks we are facing in the near future is we should provide more category information. This time we will have finished landcard mapping at first level, 10 classes. But some people would like to have landcard types for the second class and the third class. And we are also asked to have continuous updating. Okay, so they are not satisfied with only have data sets for 2000 and 2010. They would like to have data sets for 2012 2013, 15, like that. So there are many research issues to be handled. One is the best utilization of all the structural information and the spatial temporal information. For instance, it's difficult for us to distinguish, I say, grass and shrubs sometimes. So if we could have the hard information of trees and vegetations, it would be very easier for us to classify all these classes. So that we need to use new sensors, new remote sensing imageries for that. The second thing is updating. So we need to keep our database updated. So for this, we need a collaborative updating. So one of the ideas is that we ask people from different continents, different nations to work with us. So we provide all the data on the web, but people could help us to collaborate with us to update the data set of their own country, of their own region. So in this case, we should provide updates every year, even every season, something like that. The second task for us is for efficient services. People ask not only for data content service, but also geoprocessing service. So we need, for this time, we need a good cross-scale integration of all land cover data information, information for static and change information. Means we need to integrate not only global land cover sets, but also regional and municipal city level data sets. So people also ask to develop web-based dynamic geoprocessing. So there are many algorithms and models developed by the scientists, but they need their own laboratory. How do they have full easy access to all these algorithms to develop their own, what we call the chain-based services? We need also to work with all 9 GeoSPS to support their applications, modeling, simulation, and monitoring. So I would say that we have started work, but we have a long way to go. Take this opportunity, I hope that our Asian remote sensing colleagues will work with us. So join us for the validation of the data and then develop collaborative updating of the data sets for the near future. Thank you.
Thank you very much, Professor Chen Jun. May I kindly request you to remain on the stage, please? May I request Professor Chun Ji-Murai to present a token of appreciation. Professor Chen Jun, please.